Okay, let's look at this problem. So what we have here is it looks like a simple supported beam with a uniform load on it, and I want to find the internal forces at point C. So that's where we're going to cut it. You guys can tell me whether you want to work the left side or the right side. Is there any advantage to one or the other? I don't see any advantage. Both sides have some reactions that we have to get. The load on this side is uniform. The load on this side is uniform. So I don't really see any big advantage. So I'm going to work the left side. So I'm going to work the left side. I want to find the reactions at A. So let me draw on there, save a little space. I'll go ahead and assume that I have a reaction at A in the X and Y directions. And although I won't use it, I'll go ahead and assume I have a reaction at B. So using the entire free body diagram, let's find our reactions at A by summing the moments at B. Now when I do that, I'm going to have to do something about this uniform distributed load. So what we traditionally do is take a concentrated load that's equivalent to it. So you take the total area under the curve, so the magnitude is maintained. What is the area of a rectangle? Base times height, right? So that's 18 times 3. And then we'll put that load at the centroid of the loading, which is right in the center. 18 times 3 is 54. So I have a total load of 54 kips. And the distance from the right-hand side, which is where I'm going to be taking my moment, is half the total distance, which is 9 feet. So with that information, I can come over and sum the moments at point B and make sure this system is in equilibrium. I'm using right-hand rule, again, for my sign convention. So the 54 kip force creates positive moment about B with a moment arm of 9 feet. And then AY creates negative moment at a moment arm of 18. So it just says AY is half the value, right? Half of 54 is 27. So there's my reaction. Just to be complete, I'll go ahead and throw in that if I sum forces in the X direction in this problem, all I have is AX. So that's 0. Okay, so now I'm going to come down and draw my free body diagram of just this section AC, which will be the right-hand side. So there's my beam. I know what AY is. It's 27. So I'll go ahead and apply that as 27 kips. I have a distributed load. Remember the intensity of that was 3 kips per foot. The length of this beam, since I'm cutting from A to C, is 6 feet. So just like we did previously, I'm going to find a concentrated equivalent force for this section. Again, it's a rectangle, so it's base times height, so that's 6 times 3, or 18. And the distance from the cut will be half the distance, or 3 feet. Now, at the actual cut surface, I'm going to assume what? Positive axial force, positive shear force, positive bending moment. Okay, for this problem, for me, on the exam, this is 60% of the problem right there. You will not pass the exam, but you're 60% of the way there if this is correct. If this is wrong, it doesn't matter how well you do after this, right? So this is the critical part of all these problems, is taking the original information and producing an accurate description of the free body. And at this point, it's just mechanics apply statics. Right? But if you're wrong here, you're wrong. If you're right here, I like that. I reward you for that. If you're wrong here, you don't get rewarded. So at this point, we're ready to roll. So I'm a right-hand rule guy, so I will assume right-hand rule for my sign convention, and I will sum the moments at this cut and make sure it's in equilibrium. So let's do that. Using right-hand rule, what kind of moment is this? Not bending moment, what kind of moment is this? It's positive. About the cut surface, the 18 kip force creates positive or negative moment? Positive. So I have 18 kips times a moment arm of 3 feet. And then I have my reaction force, 27. That creates negative moment. And it has a moment arm of 6. You guys are going to have to help me with that. It looks like it's going to be a positive moment. I don't know what all that is. 108. 108? So 108 kip feet moment. The value came out positive, so that means it's a positive bending moment. Does that make sense that there's a positive bending moment at C?
Yes.
Mr. Abney, does it make sense to you?
Not really.
Why not? Well, before you answer that question, how will this beam bend? Won't it bend like this? Yes or no? You'll buy that? So if it bends like that, what is that? That is a smile. And it's smiling everywhere. Something that you're unfamiliar with in this class. So that means it's positive bending moment. And what do we get? Positive bending moment. Isn't that exciting?
So if this was a concrete structure, a way to keep that, is put another support in the middle?
No. If this were a concrete structure, where would you put your reinforcing steel? Top or bottom? Positive bending moment creates compression in the top, tension in the bottom. So where does the steel go?
Bottom.
Tension. So when you say that to an engineer, that this beam is in positive bending moment, then that means something to them. You've communicated an important idea to them.
Why is the shear going down now?
That's just positive shear force. Remember, we have to accept that's our sign convention. The direction of shear is not as important as bending moment.
So they're defined when you draw it, but it's your decision when you make the calculation.
Okay, I didn't understand that, Mr. McDonald.
So it's defined when you draw.
There is a sign convention for these forces.
You make your decision on when you're.
You can use whatever convention you want when you do statics, as long as you're consistent.
Okay.
All right, so let's go ahead and finish this up. I assume up when I sum forces in the y direction. So when I do that, this shear force is actually acting down as a force, so that's minus shear. And then I have minus 18 kips, and then plus 27. So it looks like my shear force is 9. So all that means is I have positive shear force of 9 kips at C.
So for the left side of that little free body diagram of AC, it would be a mirror image of that. Well,
on the right side.
The shear.
Yeah.
Got it.
Because on the okay, and that you brought that up, I will do that. I will just draw down here the other side.
I got it now.
So we'd have a reaction force over here at BY. I know we didn't solve for it, but it would also be 27. You would have a larger part of the distributed load, right? And when you got the concentrated equivalent force of that, it would be 3 times 12, or 36 kips. And it would be at a distance of half the distance, or 6 feet. But at the cut surface, positive axial force, positive shear force, positive bending moment.
Gotcha.
And if you go through the calculations, you will find that these values will be identical to those. And when I put those two pieces back together, what happens? Axial force cancels, shear force cancels, bending moments cancel.
Okay, I got it now. There, finally.
Any other questions? Okay.